Alright, hello everybody who's on currently. Give me 1 second. Oops. I'll move that for no reason. Alright. Alright, so today we are live on Instagram and YouTube. If you want me to be on Facebook, I'm going to need your phone. Alright, so it's only going to be Instagram and YouTube today. So we didn't get any questions on this this time, but we did have some questions on correlation on the last setup. So today we are going over how we do correlation work. Since that's a big thing on CFD, how accurate is it? Is what you're running accurate to what's actually going on in the real world? So what we are looking at right now is we are looking at the wind tunnel model that we tested. So if we, let me find the picture of the actual wind tunnel test and slide it over, and then we will be able to actually see what's going on. Alright, so this is a picture of when we went to the wind tunnel. So here are basically the image of what's going on the wind tunnel testing. So if you're looking at the actual CFD picture, it's kind of confusing because you have this apparatus that's held up in the wind tunnel. That's so we can test the wing by themselves in free stream, and that's because one of the big works we did was actually correlating the actual wing, and that's because full-scale car testing makes it difficult to sometimes really correlate what you're looking for without a lot more data acquisition and a lot of things to do. So this made the most sense within our budget as a small company to actually do. So what we did is we tested multiple different wings at the wind tunnel. This is our 300 millimeter V1X, and we did basically correlation work on this and verification work, which is somewhat the same thing, but not always the same thing. So when I say verification, I'm talking about verifying that the numbers we presented is actual in free stream is actually what the wing produces, and then correlation is actually kind of verifying how we do things in CFD and making sure that the numbers we're getting out of CFD is correct. Let's see. Loving my Verus made vents. Was a Fiat kid running them on my Mini Cooper track car. I painted multiple people. Awesome. I'm glad you really like your vents. So that's what this is. We also this was one of the original models that we tested for the UCW that we're slowly starting to release, that people with GT86s, BRZs, FRSs will do. And then, hold on, another question that I need to answer. Let's see, where is that? What the hell? What? Sorry, I'm getting a little mixed up here. No phone for Alright. So back to what we were talking about. So this was the original for the UCW that we tested, and this was early work on the UCW. As you can tell, it's a bottom out, and that's what that testing is. So these are the different angles of us actually testing in the wind tunnel, and what the wind tunnel gave us was forces and moments data. This is a scaled wind tunnel. I believe you can run up to I want to say a 40% model, like if you're doing a full car, maybe 60%. Don't quote me on that. Look it up on ARC's website. But we were able, because of the wing, and so there's a lot of things that go into wind tunnel data, and maybe like I'll do a separate thing on that. But basically, you have a blockage ratio you want to keep within, and so we could actually test the full wing width in the wind tunnel, even though it's a scaled wind tunnel. So, but this gave us forces and moment data that we could then correlate back to our actual wing. So then going into the CFD side of it, this is open foam. This is, we're technically looking at pair view, which is the post-processing that most people use for open foam. Since pair view is free, but pair view will do all kinds of things besides just CFD. You can look at like FEA, like geology stuff, a lot of stuff that I don't really know enough about to talk about, but you can do a lot in pair view. But it's really common to use for open foam. It's scriptable in Python, which makes it really nice because most of my images I just actually output using Python, and I don't actually open up this. It just runs in the terminal. It never opens up and just spits out the images I'm looking for. So right now what we're looking at is coefficient of pressure. I went over coefficient of pressure more last CFD, so you would actually be able to kind of look over those things. Apparently Clay said we were supposed to do this on Friday, which apparently I did not read. So what is he saying? Hold on. This might be our worst CFD Friday, sorry, just because of the fact that apparently it was supposed to be on Friday. I didn't know, but maybe we'll go over it both times. I don't know. But, so, this is what we're looking at on the CFD side of things. So, coefficient of pressure, basically the blue is low pressure, red's high pressure. 0 would be atmospheric pressure, so that's the easiest way to look at that. That's why coefficient of pressure always makes sense. You should always be looking at pressure using coefficients. And the reason is because you can compare at different velocity settings, and you'll be able to see what's going on, and velocity doesn't come into effect. Because if you really want to know what the equation is of how we're finding CP, I'll just slide this guy over, and people on YouTube can already see it. But what you're looking at is, it's basically you take pressure, you divide it by 1/2 rho v squared, and that'll actually get you CP. It's very, very easy to do. One thing that we're going to look at too that's a little bit different that we haven't looked at before is we're going to look at what's called an isosurface, and this is basically taking an isosurface. So an isosurface is basically capturing air, and it's putting surfaces all around the air of where the total pressure is 0. It's really good for like just seeing how the flow is coming off like a bluff body. You can see vortices coming off of it, and one way you can see that's obvious is you can see it coming off the end plates. So on our wing, the V1X, we have slots on the top of the end plate. We also have some things on the inside of the end plate on the bottom. It's really common to see this type of thing in Formula One. You see all these slots in the end plates, and a lot of people don't really fully understand what they do. And so slots, what they do is it's relieving some pressure from the top side of the wing, so you're losing some downforce right there by relieving some of that high pressure. However, what you're doing is you're decreasing the vortice that's caused at the top. So this is the upper vortice, and so when you're relieving some of that pressure, you're decreasing that, so you're actually decreasing overall drag. And the reason that's beneficial is because most of the downforce produced by the wing is actually on the bottom side. And because of that, relieving a little bit of, well, we just lost Instagram. So I'll wait until that comes back. I don't know if it will. Well, let's try this again. Alright, so we are back on Instagram, so we did lose Instagram for a second. So the reason you want the vents is because obviously as I was saying, the bottom part of the wing is what's making the majority of the downforce. The top side isn't really making that much downforce in comparison because high pressure is not the driving factor, it's the low pressure. So relieving a little bit of that top pressure at the top side isn't a big deal. So you do lose a little bit of downforce, but what you gain in that little bit of loss in downforce is a overall improved efficiency because you're decreasing drag. So that's the reason we have those, and you can see what they're doing in this image very well of the vortex at the top side. You can also see the vortex on the bottom side of the end plate that's also coming out. And if you're wondering what the slots are towards the bottom of the wing, that's also to help decrease the vortex on the top side. And that does not come with a loss of any sort of downforce number. So just so you know what that is. So that's kind of what we're looking at in this image. It might be a little bit easier to see if I basically take off the model part and you can see the actual surface. So that's actually what's going on right here. Alright, so we have that. And if you watched any of our video on the wind tunnel testing, you'll see that we did some basically tough testing with a wand, and you could see how the airflow comes out of the end plate, and you could see similar airflow right here. So this is a streamline. I don't use these too often in my development work, but stuff like this, it is helpful. So you can see it right here. Comes out the top. Everything works good. So that's what we're looking at. It's colored with velocity, and you can see that. Alright, so I have that, and then the main thing with the correlation is really, what do the numbers show? And let me pull that up. So right here, what we're looking at is, this is a graph of basically downforce at 10 degrees angle of attack. Hold on, make it a better thing. 10 degrees angle of attack, and comparing to different turbulence models. So let me preference turbulence models. So this is where you get into the weeds of CFD and actually need to know what you're doing to properly run CFD and make sure you're getting data that makes sense. So turbulence models basically do what they say. They model turbulence. The inherent problem with that is, why wouldn't there just be one turbulence model? The reason is because we can't. So turbulence is chaotic, and it's hard to make mathematical equations that capture chaos. So there's different turbulence models that capture different types of chaos in different ways. And a lot of automotive work is done with what's called the K omega SST, which is the blue line on the screen. An older one that was commonly used was K epsilon, and we tested the K epsilon realizable, which is a little bit different, but it's a little newer. It's similar. There's reasons to use that sometimes, and that's in the green. And then there's also the Spiller Alarmus model, which usually is just the SA model. That's what I'll say because I butchered the name of it really bad. And that's in the red. So that's also, I don't use it a whole lot. So just as a heads up, there is reasons to use it. Usually it's actually pretty good in wing only models. It actually, the K Omega works fairly close. It's a little bit better on this one. Some cases the SA model is better. There are benefits of using that over the K Omega SST besides just the accuracy reasons. But that's a whole nother type of conversation. So K Omega SST is basically our standard go-to turbulence model. There are different types of K Omega SST models. There's like the Mentor, and there's a bunch of other ones. You can get into a lot of people spend a lot of times on turbulence model, and that's what's really key to getting good CFD. It's very critical when you're talking about cars and just general bluff bodies, because that's how you know when separation occurs, and if you capture separation properly, you're going to get better downforce data, you're going to get better drag data. Some models are better for downforce, some models are better for drag capture, and all of those things. So this is where the correlation looks like. This is actually what was done in Fluent, so you can see the difference when we were still using Fluent and the correlation work. So we use this model a lot because we have wind tunnel data, and now we have two different CFD setups going in there. So that is where we use it a lot, so we can compare different runs. You do a lot of mesh sensitivity studies with it. We can do a lot of different things on that. So having the wind tunnel data is very, very critical. All right, and then let's see. And this is our direct correlation kind of with OpenFOAM. So this goes over kind of what our mesh was, the zones around our mesh, the physics model of what we ran, and then you can see the mesh sensitivity and how the values change with the amount of cells. Okay, somebody asked what curves are what. Go back to that real quick. So what we're looking at is the 300 millimeter, which is the V1X wing. This is downforce, so the left hand side of the screen is downforce. The right hand, or the x-axis is velocity, the y-axis is downforce. Then the different curves. So the black one with the triangle is the experimental from the wind tunnel. That is what we calculated from the wind tunnel. The green is K epsilon realizable, which is a turbulence model. The blue is K Omega SST, which is what we normally run on most of our automotive applications, not all. And then the SA model is in red. So that's what those curves are. And that's kind of showing the value difference between our CFD and what we found in the wind tunnel. And then you can go off. So this is, since we have the wind tunnel data, we can then do mesh sensitivity study to figure out where things are going. Somebody said that's a great result. It is a lot easier to get that type of a result though, because we were testing a very, I would say in general, a simple geometry in the wind tunnel comparatively to a full car. I would not expect a full car to be to correlate as well, and if it did, I would be very, very surprised, just because that is not something that correlates as easily in general. A lot of our full car stuff, what we've done is on the track, and that'll probably be another video sometime, is kind of how we looked at track data with laser ride heights to calculate different downforce levels. Really the best we can do on the track is look at trends and not absolutes to see if we're heading in the right direction. But with the wing testing, I think it put us in the right area of what we need. And we tested the wing up to when it started to have high separation, which actually taught us a lot on different turbulence models and different mesh densities to capture it. I'm not really going over that because that's kind of more internal of what we kind of, it's a lot of information that we learned ourselves that we don't want to just give out because of the testing. So we, on car models with a lot of separation, so say we have a dual element wing and big diffuser tunnels and a front splitter, we do things a little bit different with our mesh to make sure we're capturing stuff properly based on what we learned in the wind tunnel. We don't have 100% information on that, but we're hoping to go to the wind tunnel with a full car with a rolling road, ideally. So that is hopefully coming up that we can actually fully test. So yeah, so that was our thought, the real swiper, and that's why we did the wing, because it was something very achievable that we could actually test in the wind tunnel cost effectively, and it made a lot of sense, and we learned a lot from it to then back applying to CFD, because before that all we had was trends off track data. We did use strain gauges on wing uprights to actually figure out forces, but again, you're still dealing with messy data when you're talking about on the track, so it's still very difficult to correlate that back. So the wind tunnel made the most sense for us to try to do, and since there's a local wind tunnel here but it's scaled, we obviously couldn't afford to build a scale model of a car and test that, and it just doesn't make sense for what we do as a company. But the wing did make sense, and what was nice is we were able to test other wings that we had. We tested a competitor's wing, actually a few different competitors' wings. We also tested some other people's wings that wanted them tested, and we gave that data to them, and they were able to release that. And we didn't release their information because that's theirs, and they can do with what they want with their data. But we did compare. We brought some competitors' wings that we also then scanned and ran in CFD, and we were able to basically compare those also. So we were able to get a lot of good information from this and actually correlate it back to our CFD work. So this is specifically on open foam right now. The graph before was on Fluent. I don't really use the K-Epsilon realizable model in open foam. Actually, I've never used it in open foam. I used it very rarely in Fluent. I do use the SA model though, and the K Omega SST, and that still work. And so yeah, so that's kind of a broad overview of the thing. And then somebody on YouTube is asking what's the topic about. It is about correlation work in the wind tunnel. However, Clay did tell me that apparently this was supposed to be Friday. I didn't realize that, so we did it today. So maybe I'll do it again Friday. Maybe I'll be a little bit more polished at it. Sorry, I'm not the best public speaker. I don't really speak. I get the given this isn't public, but I'm not the most crisp, proper speaker. So if I ramble, sorry. But yeah, so that's what we're going over for the person who asked on YouTube. We are going over how we tested in the wind tunnel and correlating that back to our CFD, because that is a big area that's, I would say, is missing, especially in our market. A lot of people don't do any real correlation work. We've done a lot more that people really don't see because we don't publish a lot of it. So we've done the drive air model. If you do anything in that kind of work, you know what the drive air model is. It was developed by a university, I believe, in Germany. It's based on like an Audi and BMW and Mercedes or something all mixed together. There's wind tunnel data, there's CFD data, there's a lot of data out there that you can compare. And so we've done that work too. I just feel like, so that's just to verify that what we're doing in CFD is correct. but it doesn't always tell me if the mesh of what we're using is really capturing all the information we need, because it's such a simple model. But again, simple things still can teach you a lot. But the wing was very helpful because it is simple, but it also does have complex flow, and we were able to help correlate back to that. Let's see, we had some questions on Instagram. Wind tunnel wing looks pretty close to the ground, shown in CFD. Was there pressure gradient on the floor boundary condition? It looks close, but it's really not that close to the wing itself. To the contraption it is. Let me see if I can pull out. I didn't pull the floor, but I do have the full model here. Let me pull the lower wall. I'll add the lower wall in so you can kind of see how close it is, and you can see how then the pressure is affected. It was not rolling road. We didn't have the rolling road moving, at least I believe. Don't quote me on that. I'm 80% sure we didn't have the rolling road running at the time, because we didn't have any actual things running. It does have boundary layer suction in the front though also, so there is that. Let's see, wing may have influenced the results. That was primary goal because you guys are well. Yes, so we are aware of that. Let's see, did it load? Alright, it looks like it loaded, so let me actually extract that out. So you can, apparently it didn't fully load. Here we go. Pulling the lower wall. Of course, it's because so normally if you're using ParaView and you did that and you already calculated CP, it would already have it, but I pulled in the model because I break these up with using VDK, so that whole thing's a patch. It makes it easier for post-processing. I didn't do the lower wall, so I will run the same equation so we can keep it so you can see what the pressure's like on the actual floor. So how we modeled the tunnel is based on how they recommended. So ARC also does CFD, and they use Elements, which is based on OpenFoam. Looks like pretty awesome software. It's basically a GUI to OpenFoam, and then they have their own meshing and things like that that are different than the OpenFoam variety. And it was developed with ARC and another company called Ingis. I believe that's how you pronounce it. And so yeah. But this is how they recommended setting it up. Like tunnel size and everything like that. So there we go. So you can now see how the floor is affected. So it is a low pressure zone around, I would say peak around 0.4 on minus 0.4 on CP. So yeah, I guess that kind of is the end of this. Maybe I'll go into it again on Friday, since apparently that's when I was supposed to do this. I don't know, because Clay is our sales and marketing guy. He is on vacation, so he was setting all this up, and it was probably just a miscommunication between him and I. So but does anybody else have any other questions? And if you do have any questions, feel free to send us the questions, because maybe I will do this again Friday, since that's when we said we were going to do it, and I'll keep this one short. And if you do have any questions from going over this, then send them, and I will try to answer them the best I can and be as transparent as I can about what we do. However, we don't show everything. We just try to show enough to try to educate people and show that we're doing what we feel is proper for correlation work and how we run CFD. So if no one else has any other questions, I'm going to end it for today. Thank you. Bye.